Hi everyone. Today we shall see how to find minimal cover given a set of functional dependencies. So let me start. If you look at, we'll begin with the algorithm first and we shall see the application of it in a problem scenario. So what is this minimal cover? In my previous video, I have explained to you what is a cover. Cover is basically a set of functional dependencies F from which if you can deduce the functional dependency of another set of functional dependency E, then we say F covers E. But while doing so, we need to make use of minimal set of functional dependencies. So given a set of functional dependencies, is it possible to minimize the number of functional dependencies to find a cover? So that's a problem scenario here. Let us look at the algorithm first. So if you look at the algorithm which is given here, algorithm 15.2, the input to this algorithm is simply a set of functional dependencies E. So we need to find out the minimal cover F. So initially we assume that the given set of functional dependencies themselves are the minimal cover. Then for each of the functional dependency of the arrow X, arrow Y, where Y contains A1, A2 up to AN, second step in this algorithm is to write each of these functional dependencies in what is called as a canonical form. That is, you have to write X arrow Y as X arrow A1, X arrow A2 up to X arrow AN. So if any functional dependency of the form X arrow Y in which Y contains more than one attribute, then we have to split that using the decomposition rule and write it in canonical form. That is, the right hand side of every functional dependency should contain only one attribute. So that's the second step here. So what next? The next step is for each of the functional dependencies of the form X arrow A, see if you can eliminate one of these functional dependencies or try to reduce the number of attributes on the X side. So if you remove one attribute B from X and try to find out whether this functional dependency still in F, then attribute B is redundant. You have to reduce the number of attributes on the X side as much as possible. The second thing is, if the functional dependency X arrow A itself can be removed, that is F minus X arrow A, if it is equivalent to F, then we don't need X arrow A. So we have to do a minimization step here so that X contains minimal set of attributes, and also if possible X minus X arrow A can be completely eliminated from the set. So we have to apply this and try to find out. In step number 4, each of the remaining functional dependencies X arrow A, where X contains maybe just one attribute. In the previous step we have eliminated X arrow A in which X has more than one attribute. So those other functional dependencies in which X has only one attribute, see whether that is really required. If you find that F minus X arrow A is somewhere equivalent to F, then X arrow A is not required. So unwanted functional dependencies can be eliminated. So when you do this, we'll end up with a set of functional dependencies of the form X arrow A are all minimal set. Okay. I'm sure you are not followed much of it. Let us see the application of the same in an application scenario. So he has taken a functional dependency set which is B arrow A, D arrow A and AB arrow D. Now let us assume that the minimal cover F is equal to E. It means all of these are part of the minimal cover F. Now if you observe these functional dependencies 1, 2 and 3, each of them is of the form X arrow A. It means they are already in the canonical form. So we can do away with step number 2 and directly go to step number 3. Now you have to choose that FD which has more than one attribute on the X side, that is AB arrow D. Now we don't know whether A is essential or B is essential. We have to eliminate one of these. If we can do that, then we see that we will have a minimal functional dependency. Now to implement this, what you have to do is take the first functional dependency B arrow A. So if you add B on both sides, we get B into B as AB. So B into B is B itself. So then you have AB. Now this is the new functional dependency derived from 1. So let's call it as 1 dash. Now if you observe 1 and 3 or 1 dash and 3 is AB arrow D. But now we have a transitivity here, B arrow AB and AB arrow D. So we can readily recognize this as a transitive dependency. So we can write it as B arrow D. Now this shows that we directly can determine D using just B. We don't require A. So you can eliminate A from this X side. So what we are left with is three functional dependencies, that is B arrow A, D arrow A, and B arrow D. So as a result of that third step in our algorithm, we got this. Now let us go to the fourth step. Can you eliminate any of these functional dependencies somehow? If you observe the three functional dependencies, 1, 2, 3, if you observe from this functional dependency that from 2 and 3, we observe that B determines D and D determines A, again you find there is a transitivity. Okay, so again you find there is a transitivity and we can write it as B arrow. So we can eliminate the functional dependency in this list. B arrow can be derived, so we can eliminate this. So what we are left with is F, which is equal to D arrow A and B arrow D. So these are the only functional dependencies which are required. So this is the minimal cover. Okay, so hope you understood the method. I'm sure still you have some of the doubts as to why I added B only on the both sides, because I wanted to bring in the transitivity between A arrow AB, B arrow AB, and AB arrow D. So you have to recognize some functional dependency which is on the X side, that has to come on the right hand side of another functional dependency. To get this, we have to add B on both sides. So probably with practice, you'll be able to know what to do to get the minimal cover. So let's take one example from the question paper. That is, you see that this problem is given to you, question number 8b. So your functional dependencies are given as F. So in fact, we can take it as E here, A arrow C, AC arrow D, E arrow AD, and E arrow H. So these are the functional dependencies which are given to us. Now, by applying the step number 2, first step of course is functional dependency which is minimal cover F is equal to E itself. It means you have to assign E to F and write each functional dependency in the canonical form. So you observe that this functional dependency is not in canonical form. So I would write it as A arrow C, AC arrow D, E arrow A, E arrow D, and finally E arrow H. So now you see that all are in the canonical form. So only functional dependency which is put to test in step number 4 is AC arrow D. Can I do away with either A or C somehow, is what I have to see. So let us see how I can do this. Now take this functional dependency, and if you add AC on the, now take this functional dependency A arrow C, and we need to check whether I can eliminate A or C. So what we can do is see if there is a possibility of a transitivity. So we know that AC is determining D. So if AC can determine uh, uh, if something else can determine AC, then we can do the transitivity. So by adding A on both sides here, A arrow A equal to A dot C. So you'll see A arrow AC. Now this is a new functional dependency, but we already have AC arrow D. So you observe there's a transitivity here. So you can eliminate the middle part and you get A arrow D. So D can be determined only from A, you don't require C. Okay, so I have eliminated C. So what we are left with is A arrow C. AC arrow D is eliminated, so we get only A arrow D. Then we have E arrow A, E arrow D, then E arrow H. Okay, so if you observe anything which is possible here, now A arrow C, A arrow D can be clubbed as A arrow CD, and E arrow A, E arrow D, all these three can be clubbed as E arrow ADH. So we get the minimal cover as simply A arrow CD and A arrow CD and E as AD. Okay, so is there anything possible? Yeah, hello. There's a small addition here. So we found out the set of functional dependencies here. However, there is one more elimination possible. That is, we know that here we have E arrow ADH. We can write it as E arrow A and E arrow DH by decomposition rule. But if you see the transitivity here, E determines A and A determines CD, so implies that E determines CD. And we have E determines DH. So the minimal cover here would be E arrow CDH. So one extra D can be eliminated. So only functional dependency that is needed as a cover is E arrow CD. So if you have liked my video, click on the bell icon and on the like button and subscribe to my channel. Thank you.